We discussed last time a technique called selective population inversion. The idea was to do a polarization transfer from a more sensitive nucleus to a insensitive nucleus. So, for example, if I have a 2 spin system, we have 2 lines here and then I have another like this, and this is more sensitive. So, this has more intensity, and this we saw, okay, let us say we have this intensity of these 2 lines as 2 delta dou delta, and this one has capital 2 delta, these are more sensitive. Then we saw that if I do an inversion on one of these transitions, let us say I do an inversion here. Inversion means I apply a selective 180 degree pulse on this particular transition. So, when I do this transition, so as a result of this inversion I will get spectra where the intensity of these 2 weak lines, they get enhanced. So, let us say these ones were x1, x2, and this is these ones are a1, a2, and if a1 is inverted, then what is kind of a spectrum I will get? We saw that we will get a huge enhancement in the intensity of these signals. So, what we saw was this will become get a signal like this for x1 and a signal like this for x2, and for a1 it will be like this, and a2 also it will be like this. So, because we have inverted this a1 transition, so this will have the intensity of minus 2 delta and this will have the intensity of plus 2 delta. This signal has an intensity of minus 2 delta plus 2 delta, and this one had the intensity of 2 delta plus 2 delta. Of course, this one should go longer compared to this, there is no space there. So, this you can extend it below above there. So, therefore, you see this there is a substantial gain in the intensity of this signals, and here of course delta is much greater than, capital delta is greater than delta. So, this was a population transfer. As a result of the population transfer from the A spin, one of the transitions, then we get a significant enhancement in the intensities of the X transitions. However, we had this problem that okay, we have positive negative signals here, and selectivity is quite an issue. So, applying a selective pulse was an issue, and therefore, we had some difficulties here. That is, what were the difficulties? Selectivity was an issue, selectivity is a problem, and we cannot do it in crowded spectra. Okay. Then we also have the positive negative signals. Okay. So, in order to get over this problem, so there was a new technique which came up, which is called as INEPT, insensitive nuclei enhancement by polarization transfer. So, the experiment is quite well described here. I will go through it stepwise, and we will use, you will see that we will use here the principle of SPI also here at this point, and we will see where. I will explain to you where we do use this. Pulse sequence goes like this. So, this is called insensitive nuclei enhancement by polarization transfer, or in short INEPT. Experiment starts like this. So, you have the A spin here and the X spin there, and the X spin is supposed to be the less sensitive one and the A spin is supposed to be the more sensitive nucleus. Okay. So, now we apply a hard pulse to A. Hard pulse means it is not selective anymore. So, you invert, you apply a hard pulse, that is called as a hard pulse. All the transitions of A spin are excited. So, we apply a 90x pulse to the A spin, wait for a period tau, and then you apply simultaneously 180 degree pulses to both the A spin and the X spin. And this is particularly easy if the A spin is for example a proton and X spin is like a carbon. and then it is very easy to do it, because these are two different channels, and to apply pulses on two different channels is not a problem at all, because independently they work. So therefore you can apply without any issue of interference between the two. Then you wait for the same time tau again, then you apply a selective, not selective, now hard again 90-degree pulse on along the y axis here and the 90x pulse here. Here it does not matter which one you take, but more importantly this has to be a y. If this is x, this has to be a y. So therefore you make this sort of a pulse sequence, and then you will see what happens, that you will get a substantial enhancement of the X magnetization, and that is what you will detect here. Okay. Now let us try and analyze this. Okay. So how does this work? Basically if you recall the spin echo experiment, we had this spin echo from this is 90 180 90 tau 180 tau, this is the spin echo sequence. At the end of this 2 tau we have the echo appearing. Okay. And then you apply the 90-degree pulse on both the channels, the A channel and the X channel, to transfer magnetization from the A spin to the X spin. How does that work? Let us see here. Let us assume that we sit on the rotating frame of the A spin, and these are the time points indicated here 1, 2, 3, 4, 5. Okay. So before this 90-degree pulse, what is the magnetization? The magnetization is along the z axis. At this point the magnetization, this if I call this time point as 0, the magnetization is along the z axis. If I say here, if the time point is 0 here, the magnetization here is along the z axis. Now when I apply a 90-degree pulse, the magnetization comes onto the minus y axis. Now notice I am applying a pulse only to the A spin. Therefore I need to consider only the A spin here. Now if it is coupling between A and X, this will be transition, there will be two transitions A1 and A2, and both magnetizations are along the y axis, minus y axis. So I just still represent that as A1 and A2. These are the y magnetizations corresponding to the A1 and the A2 transitions. Okay. Now what I do during the period 1/4j, what will happen? These ones will start precessing. Now as I said, I am sitting in the middle of the A1 and the A2 transitions. When I am, this is exactly the spin echo sequence. The spin echo sequence meaning, so I have this A1 and the A2 transitions here. I am sitting here. If I am sitting there, so therefore the one of them goes faster, other one goes slower. Therefore these ones will move in the two opposite directions. So these A1 and the A2 will move in opposite, one will move like this, other one will move like this, because I am sitting in the middle. Now it will move over a certain angle, and what is that angle? That angle is given by what is the frequency difference between the two and the delay you give, because this separation between them is j, and therefore 2 pi j and the tau we give, that is the angle with which it will rotate. Okay. So the angle with which will rotate is, let me write here, angle theta, what it will rotate is 2 pi j tau. Okay. So j is the frequency difference between the two, therefore the separation between them will be 2 pi j tau. So if I say tau is equal to 1/4j, how much will be the angle? If it is 4j, then it will be pi by 2. So the angle between these two will be pi by 2. At this point it is pi by 2. Okay. So now I am applying a 180-degree pulse on the A spin. So A spin what apply 180-degree pulse, this A2 transition will come here and the A1 transition will come here, that is what is indicated here. Okay. And they will continue to move in the same direction, this will continue to move in the same direction like this, A1 will go like this and the A2 will go like that. Now the trick is here, I apply also 180-degree pulse to the X spin as well. Remember what happens if I apply 180 pulse to the X spin? It will invert the X and it will invert the alpha and the beta states of the X spin. Convert alpha to the beta, this 180-degree pulse converts alpha to the beta of the X spin. So when that happens, these two transitions will get interchanged. A1 becomes A2, A2 becomes A1. Therefore when you have this will become A1 here, this will go in the opposite direction, this A2, this will go in this direction now. Okay, if this one the slower becomes faster, the faster becomes the slower. So therefore now this will go like this and this will go like this. Okay. So now during the next 1/4j, what will happen? They will again move away from each other and another pi/2 phase angle will be introduced. So this was pi/2 here and this was also pi/2. This was also pi/2, we did not do anything here. This was also pi/2, but when it moves, now it is pi. During the next one, another pi/2 is added there. So therefore now they become opposite to each other. So they are along the now the x and the minus y axis, x and the minus y axis, right. So now we apply a 90° y pulse, a 90° y pulse here onto the A transition. So that means I am applying a pulse along the y axis. So what will happen to these? These two which are along the x and the y, they will now go to the z axis. On the positive and the negative z axis, they will come along this. Okay. Now we compare this situation with what we had here in the beginning. In the beginning the two transitions were at time point 0, at time point 0 where they were at time point 0, these two transitions were both along the z axis, right. Let me use that same color. At time point 0, both the transitions of A1 and A2 magnetizations were along the z axis. This is the z axis, A1 and A2. Magnetizations corresponding to this, they were along the positive z axis. Now what I have achieved here at this point, I have done inverting one of these, inverting the A2 transition here. The A1 is kept up there like that only. Nothing has happened to the A1 and the A2 is inverted. This is like SPI, populations are inverted as in SPI. You see one transition is inverted. Okay. So therefore I get the same benefits as I will get from the SPI. Okay. How much do I get now? So if we look back, what did we have in this? In this one I had minus 2 delta plus 2 delta and 2 delta plus 2, the same win I will have there also, and this will be minus 2 delta plus 2 delta, that will be present there. Okay. So here therefore if when I apply 90 y pulse to the next pulse, if I apply, the transitions of the A spin have gone on to the positive and the negative z axis, and the x now x spin, this is the first time applying a 90 pulse. Therefore the x magnetization will now come on to the transverse plane, See, before this point, at this time point 4, these two transitions, the intensities of these are along the z axis only, right, these added is along the z axis. Okay. So at this point there is no transverse magnetization of the x spin, it has got the populations of the 8 spin. It has got at this point the x spin, let me use a different color, the x spin have both the transitions along the z axis, but one of them is like this, other one is like this along the z axis. Part of this has come from the A spin transition. How much has come from the A spin? From the A spin, as we said, if it is 2 delta minus 2 delta, to begin with it was 2 delta. So let us say this was 2 delta plus 2 delta and this was minus 2 delta plus 2 delta. This is at this point after the 90° y pulse, this will be at this point. Okay. Now notice here, but I have also applied a 180° x onto the x spin. So therefore what was 2 small delta here, so here there was the two transitions of the magnetizations corresponding to the x spin were like this, and these were 2 delta and 2 delta, and but this is now inverted to this 2 delta, 2 delta, minus 2 delta, minus 2 delta. This is coming directly from the excitation of the x spin. This is coming from the excitation of the x spin. At this point the x magnetization along the z axis was corresponding to 2 small delta, 2 small delta as it in this one. Now this 180 x pulse makes this to minus 2 delta, minus 2 delta with regard to the populations. This will carry forward, therefore I have to add that here, whatever is coming here will be added here. So in that case what I will get? I will get minus 2 delta, let me add with a different color. So then I will have to add here minus 2 delta to this and minus 2 delta to this. Okay. So therefore what I got? I got 2 delta and minus 2 delta. As a result I get, I will use the same color here, I get this is 2 delta and this is minus 2 delta. That is what I have shown here. That is what I have shown here, x1 and x2 as they are coming, these are identical to this. Okay. So let me put a circle here to explain this to you. So this is the same. So when I do this, the initial magnetization is along the populations are corresponding to this, and when I apply a 90x to 90x here, this magnetization gets transferred onto the transverse plane. So then I measure it, then it will be 2 signals of equal amplitude but along the positive and the negative z axis. Okay. So how much is the enhancement here? What was delta earlier, small delta earlier is now capital delta, right. So therefore the enhancement is, so therefore the, let me write, do I have it? Okay. So therefore in the AX case the enhancement is by factor delta by delta, and these ones are dependent on the populations, these are dependent on the populations or the sensitivity. Therefore this will be proportional to gamma A by gamma x. Okay. So this is the kind of an enhancement you will get for a simple 2x spin system. Okay. And this will be, for example, this will be like factor of 4 for carbon 13 and factor of 10 for nitrogen 15. So this is a substantial enhancement. Okay. So now what happens, but however we still have this problem of positive negative lines and that continues. Okay. So we have not gotten over that problem, but we have gotten over the selectivity issue. We do not need to apply a selective pulse anymore, we are applying a hard pulse. By applying the hard pulse we have got the same result, intensity enhancement and similar intensities for both the lines. Earlier you remember in SPI we did not have similar intensities for the 2 lines, they were slightly different. Now here we get similar intensities for the 2 lines in the X spin. Now what happens? Suppose I consider an A2X system, and this is the experimental spectrum here which shows exactly that point here. See, these are identical lines with similar intensities, similarly here, and of course we have more complex spin systems here because this is not only AX but also we have A2X, A3X and things like that. Now of course in real life, of course you not only have an AX, not only have a CH group, but you also have CH2 groups and CH3 groups and things like that. So what happens in the case of a CH2 group, and that is indicated by this A2X spin system. The A2X indicates like a CH2, X is the C and A2 is the H2. But the transfer is considering, we consider the transfer from the individual protons at a time, So therefore how will we analyze this A2X system? Consider the X, consider the x, let to analyze this A to X system, consider the x, okay. Now this one is now split because of one coupling, one transfer into two lines. Like this, equal intensity. So when I apply, when there is a next coupling, there is a, this is due to the 1JX coupling, 1JAX coupling. The second coupling, what it will do? The second JX coupling will split these individual lines into two again. It will split these individual lines into, but now this will be in phase splitting. This will split like this, and the other one will also split, and that will happen, use a different color here, and that will happen like this. Okay, the second line. So this line has split into these two, and this line has split into these two because of the another coupling, the second coupling, because there are two A's there. The first A has resulted in this antiphase separation, this is called as antiphase separation, and this now is split further due to another coupling of the X to the second proton here, okay, and that results in splitting. Now what happens? These two central lines will cancel, this will cancel. So then I will have only two lines. Now this will result in one line here, and now there is a gap and there is another line here. So then the center there is nothing. That is what will happen in the case of A to X. The central portion has got 0. This separation is now 2 times JAX. From here to here is not JAX but 2 times JAX. Okay. The central line which is there, here it was JAX, here it was, okay. In the single case there was a JAX. Now this central line has vanished, therefore in this case I get a 2 times JAX, okay. So that is explanation for that. Now you can consider further, for suppose there is a A3X. If there is a A3X, these two will split again. These two will split again. So if you have another J, then these two will again split as like this, and then the other one will also split, but now it will come closer because it will go on to this side. This is what will happen for an A3X, okay. So that A3X, so therefore this will be the A3X and this will be the A2X. We still have the positive negative signals, and the total separation from here to here is of course 3 times JAX. Separation from here to here will be, because there are 3 couplings, therefore there has to be 3 times JX. From here to here should be 3 times JAX, okay. So that is this is 1 JAX, and from here to here is 2 times JXA. These are one bond couplings, remember, XA. So these are one bond coupling, therefore there is a total of 3 bonds. So therefore A3X spin system will appear in this manner, A2X will appear like this, and this is again a disadvantage for the inept sequence because the middle sequence is gone. Now you may tend to think that if I get a spectrum like this is actually an AX with a coupling constant which is twice that of the normal coupling, okay, one bond coupling, which is not the case. It is actually an A2X, but this is because of the sequence you will get a separation which is twice that, and the central line has vanished, okay. So this is, while you have circumvented the problem of sensitivity, the problem of selectivity problem, you have still got the antiphase problems and you have some missing signals in the middle. So that will be a kind of a disadvantage, okay. So therefore here we will have missing signals, missing central line. Okay. So this is what I indicated there with regard to the inept sequence, how it will increase the sensitivity. So therefore the inept use non-selective pulses, okay. So, you have gain with identical intensities for the two lines in the X doublet. Okay. And the gain is by the fact is gamma A by gamma X. Okay, so this much gain we will get in the case of inept. Okay. Now the disadvantage of course will be are still disadvantages. Disadvantages are, so you have the positive negative signals still present, but missing line in A2X systems. Okay. So, to get over this problem there was one more technique which came into existence, and this is called as the refocused inept. Refocused inept, what it does, it is until here it is the same as the inept, okay. Until here it is the same as the inept, and then we have introduced another block here which is tau, it can be tau dash or it can be tau or tau also. In the simplest case it is tau and tau. So then what happens here? So at this point if I draw the X transitions, if you recall the X transitions were along the X axis or the Y axis, whatever that is. So if this is minus Y, this is minus Y, and the two transitions were oriented like this, and such a signal is called as antiphase magnetization. This is called as antiphase magnetization, because two transitions have opposite phases. Now what we have done is you have continued the spin echo in an identical manner. You trace the tau and tau, suppose tau dash is equal to tau, tau dash is equal to tau, you are simply repeating that same sequence. Therefore as a result of this, during the next 2 tau period, what will happen? This one will again clear another 180 degree phase difference, okay, and then they will become oriented like this. They will refocus. So they will come here along, they will refocus. The separation 180 degree phase difference which was there, that would be gone, okay, because it rotates by another 180 degrees. Another 180 degrees meaning they will come back in phase. This is called the refocusing. So when they refocus, now if you now take a spectrum of this, you will get in phase lines, because the magnetizations are not along the opposite directions, right, and this magnetization here was like this and like this, and when you do a refocusing, so you will get magnetization along this axis here, and we will get pure phase. After you do phase correction etc., you will get in phase magnetization. This is called as in phase magnetization. Now of course you notice here, of course the tau dash is a variable, tau dash can be optimized for certain purposes, we will not go into those details here, and there is also one other pulse which is applied as a modification to a refocused inept is called as the inept plus, and this is a modification to remove some artifacts. And this actually pulse sequence is called as inept plus. With that modification it is called as inept plus, but we will not go into those details here, that requires more of theoretical calculations, and but this is enough to understand that okay, we can actually do a refocusing. If you refocus, what is the advantage? We collect the data here, we collect the data, then magnetization is now in phase, therefore we can decouple it also. So now if you do decoupling, you can do decoupling here, you can decouple, they can get a one line. You can get one line which has the sum of the intensities of these two. For decouple, so this is possible. This decoupling can be introduced here. This is decoupling. So the proton can be decoupled while you are observing the X. When you observe the X, now you get a very huge gain in the, so now the splitting is gone, you do not need this splitting. This is one bond coupling, one bond coupling is not of much use. So therefore you can remove that coupling, then you will get a single line for the particular carbon or the nitrogen or whatever you are talking about. So you will have a substantial gain in the signal to noise ratio, and this is the benefit of this refocused inept. Every time you want to decouple, you have to remove this antiphase character, bring them into in phase. In phase means they both go in the same direction like this. So therefore then you can collapse them. If they are like this, so you decouple, it becomes 0. But if they are going like this, if they are two like this, if you decouple, they will become like that, and of course they will add on intensity. So there will be a substantial gain in the intensity because of that. Okay. So and here is an example of such a spectrum, is a practical example. You can see all in phase lines and with much higher signal to noise ratios, intensities, and all multiplet structures will get retained. So you will not have any problems with the missing peaks, and all the things will be retained. So this is the ideal technique one can use, and most of the time this is what one uses, all multidimensional NMR experiments. Okay. And I think we will stop here with the polarization transfer. Okay.